Okay, in this lecture we're going to cover the first part of our section 4.3 material on partial derivatives. So in chapter 4 we've been looking at functions of multiple variables, and a lot of the problems that we've been considering we're working with functions of two variables, say x and y. And in this section we're going to talk about how to differentiate these multivariable functions and define something called a partial derivative. So to introduce the definition, let us suppose that a function f of two variables, x and y, is a function of two variables. So we would define the partial derivatives of this function f with respect to x and y as follows. So first off, let me talk about the notation that we're going to use for partial derivatives. So if I have a function that depends on two variables x and y, I could differentiate with respect to either variable. And the partial derivative of this function f with respect to x will be denoted as f sub x of xy, and the partial derivative of f with respect to y will be denoted as f sub y of xy. Now these are defined in terms of limits. The partial derivative of f with respect to x is given by the limit as h approaches 0 of the difference quotient f of x plus h y minus f of xy all over h. So we're looking at the difference in the values of the function f at the points x plus h, y, and xy over h, and then letting this value of h approach 0. And the partial derivative of f with respect to y is defined similarly as the limit as h approaches 0 of f of x y plus h minus f of xy all over h. So this will be our definition of partial derivatives of f with respect to x and y, provided that these limiting values exist. So what exactly are we measuring here? What do these partial derivatives represent? Well, just like derivatives of single variable functions, they represent rates of change or instantaneous rates of change of the value of a function at a particular point, as we're making a change either in the variable x only or a change in the variable y only. So these partial derivatives will give us how quickly our function is changing if we make a change in the variable x or if we make a change in the variable y. What is the corresponding rate at which the values of our function change? So let's look at a first example. We're asked to find the partial derivatives f sub x and f sub y of the function f of xy, which is this polynomial function of two variables. And it says here that we're using the limit definition to find these partial derivatives. So let us start with the partial derivative of f with respect to x. So here, typically instead of writing f sub x of xy, we might just write f sub x. Now this is defined as the limit as h approaches 0 of f of x plus hy minus f of xy all over h. So for the first part of our numerator, we're evaluating the function f at the point x plus hy. So everywhere that we had an x, we will be replacing it with x plus h. So for our function, we'll have x plus h squared minus 3 times x plus hy plus 2y squared minus 4 times x plus h plus 5y minus 12. And then we're subtracting f of xy. So that is, we're subtracting the function itself, x squared minus 3xy plus 2y squared minus 4x plus 5y minus 12. And this entire expression is being divided by h. So we have the limit as h approaches 0 of, now for notational simplicity, rather than writing this as a fraction throughout my work, the division by h I'm going to consider as multiplication by 1 over h out in front of my numerator. Now expanding the expression that we had for f of x plus hy, we have x squared plus 2xh plus h squared minus 3xy minus 3hy plus 2y squared minus 4x minus 4h plus 5y minus 12. And then we were subtracting f of x, which is again x squared minus 3xy plus 2y squared minus 4x plus 5y minus 12. So there are several terms which will cancel out with one another here after we expand. The first of which would be our x squared with the minus x squared, then the negative 3xy minus a negative 3xy, the 2y squared minus 2y squared, negative 4x minus a negative 4x, the 5y and minus 5y, and lastly the negative 12 minus the negative 12. So altogether we're left with the limit as h approaches 0 of 1 over h times 2xh plus h squared minus 3hy minus 4h. So dividing this expression through by h, we are left with the limit as h approaches 0 of 2x plus h minus 3y minus 4. So taking the limit as h approaches 0, well, this term involving h tends to 0, and we're left with the function 2x minus 3y minus 4. So this would be the partial derivative of our function f with respect to x. Now similarly, to find the partial derivative of f with respect to y, we would be looking at the limit as h approaches 0 of f of x y plus h minus f of xy all over h. So for the first part of my numerator, I'm taking the function and evaluating at x, y plus h. So that means everywhere I had a y, I'm replacing it with y plus h. And so we have x squared minus 3x times y plus h plus 2 times y plus h quantity squared minus 4x plus 5 times y plus h minus 12. And then we're subtracting f of xy, which was x squared minus 3xy plus 2y squared minus 4x plus 5y minus 12. And this entire expression is being divided by h. So as with the partial derivative with respect to x, instead of thinking about this as a quotient throughout for notational simplicity, my division by h let me think of as multiplication by 1 over h. And expanding the first part of my numerator, I would have x squared minus 3xy minus 3xh plus 2y squared plus 4yh plus 2h squared minus 4x plus 5y plus 5h minus 12. And then we are still subtracting the quantity f of xy, which was again x squared minus 3xy plus 2y squared minus 4x plus 5y minus 12. So again, canceling some like terms, well, our x squared minus x squared cancel. The negative 3xy minus a negative 3xy cancel. The 2y squared minus 2y squared. Negative 4x minus the negative 4x. 5y minus 5y. And lastly, the negative 12 with the negative 12. So we are left with the limit as h approaches 0 of 1 over h times negative 3xh plus 4yh plus 2h squared plus 5h. So dividing through by h, we have the limit as h approaches 0 of negative 3x plus 4y plus 2h plus 5. So taking the limit as h approaches 0, our term 2h tends to 0, and we are left with negative 3x plus 4y plus 5 for the partial derivative of this function with respect to y. So one thing to notice here in our definition of, our limit definition of the partial derivative is that when we're calculating the partial derivative of f with respect to x, in our limit definition, there is no change in the variable y. So for instance, in the numerator, we're looking at the difference of f of x plus h y minus f of xy. So the only difference in our numerator is in the variable x, where we've got x plus h and x. But y is treated as a constant throughout that equation. And similarly, if we're differentiating f with respect to y, for our limit definition, our numerator is f of x y plus h minus f of xy. So the variable x in that equation is being held constant. Now, also notice when we look at the results that we found for our partial derivatives in this first example, we had f of x, or f sub x of xy was the following function. So I claim that we could have gotten this directly by just looking at our function and using the rules from for differentiation from Calculus 1. So for instance, if we want to differentiate f with respect to x, using the definition, we said we're going to treat y as a constant. There is no change in the variable y. So looking at our function here, if we differentiate this with respect to x and think of y as being a constant, well, the derivative of our first term, x squared, would be 2x. The derivative of minus 3xy would be minus 3y, if we're treating y as a constant. And then the derivative of this 2y squared term would be 0, if y is a constant. The derivative of negative 4x would be negative 4. And then if y is a constant, the derivative of 5y minus 12 would be 0. So we get exactly the expression for f sub x that we found using the limit definition, but with a lot less work. So in the case that we were looking at the partial derivative of f with respect to y, well, in the limit definition, we said we were treating x as a constant. X is held as a fixed value, and we're looking at how the function changes as y changes. So if we were to just look at our function and think of x as a variable, x as a constant and y as our variable, the derivative of x squared would be 0, since x is a constant. The derivative of negative 3xy would be negative 3x. The derivative of 2y squared would be 4y to the first power. The derivative of negative 4x, if x is a constant, would be 0. The derivative of 5y would be 5, and then minus the derivative of our constant 12 is 0. So notice that that's exactly what we found for the partial derivative of f with respect to y using that limit definition, but it was much less work. So now that we've looked at this one example of finding the partial derivative of a function using the limit definition, and we've observed that we could have obtained the same thing by just treating the variable x or y as a constant and differentiating with respect to our other variable, we can arrive at the following result: how to find the partial derivatives of a function of two variables x and y. So just as we had described in that first example, to find the partial derivative of f with respect to x, we're going to treat the other variable, y, as a constant and differentiate f with respect to the variable x, the same way that we would in Calculus 1. And to find the partial derivative of f with respect to y, we would treat x as a constant and differentiate the function f with respect to y. So before we look at some other examples, let me make a little comment about notation for partial derivatives. So there's several different notations that we could use for a partial derivative of a function. So let's summarize some of them. Here, if z is equal to some function of two variables x and y, then we would say the partial derivatives of f with respect to x and y could be denoted as follows. So the first notation we've already introduced, this subscript notation. We could say the partial derivative of f with respect to x or y would be denoted as f sub x or f sub y. Or since we were saying z is equal to the value of this function, f of xy, we might also use z sub x or z sub y for those partial derivatives. Now, another notation that we could use would be similar to the Leibniz notation for the derivative of a single variable function. So let's say that we wanted the partial derivative of f with respect to x. We could write it as del f over del x or del z over del x. So it's similar to the df dx notation that we had seen in Calculus 1, but for partial derivatives, instead of a df dx, we use this symbol which is referred to as del. So we would say del f over del x or del z over del x. Or similarly, for the partial derivatives of f with respect to y, we could use the notation del f over del y or del z over del y. Now the last notation that I'll introduce here, we won't use hardly ever for our course, but you would see this notation in some engineering or physics textbooks. So just so you're familiar with it, the partial derivative of f with respect to x or y could be denoted as d sub x f or d sub y f. So let's look at some examples of finding these partial derivatives of a function and then we'll consider a geometric interpretation. So in our next example, we're asked for the partial derivatives of f with respect to x and of f with respect to y for each of the functions given. So in part A, we have f of xy is some polynomial function of x and y. So if I want to find the partial derivative of f with respect to x, I would treat y as a constant and differentiate with respect to x the way that we typically would. So for x cubed, our derivative would be 3x squared plus x squared times y. Well, the derivative of x squared would be 2x, and then we're multiplying by some constant y on the end. Plus, we have x times y squared. Now the derivative of x is 1, and then we're multiplying by some constant, y squared. And then minus, well, if y is a constant, then 3y cubed is a constant, and the derivative of any constant would be 0. So this would be our partial derivative of f with respect to x. Now similarly, the partial derivative of f with respect to y would be found by treating x as a constant and differentiating with respect to y. So our first term, x cubed, would be a constant if we're thinking of x as a constant. So its derivative would be 0. Then we have a plus x squared is a constant times the derivative of y would be 1. Then plus we have a constant x times y squared. Now the derivative of y squared would be 2y. So just rewriting the 2 out in front of our constant terms x, I would have 2 times x y to the first power. And then minus our derivative of 3y cubed would be 9y squared. So these are our partial derivatives. Now in part B, we have a function f of xy is the natural log of some polynomial function of x and y. So in order to differentiate this composite function, we're going to have to make use of the chain rule. So if we want the partial derivative of f with respect to x, well, recall that the derivative of the natural log of stuff is given by 1 over that stuff. So in this case, 1 over 3x squared minus xy. And then using the chain rule, we have to multiply by the derivative of the inner function with respect to x. So here we're treating y as a constant. So the derivative of that inner function with respect to x would be 6x to the first power minus 1 times the constant y. Or writing this as a single ratio, we have 6x minus y over 3x squared minus xy. And the partial derivative of f with respect to y is given by, well again, differentiating the outer function, the derivative of natural log of stuff is 1 over that stuff times the derivative of the inside function with respect to y, which would be negative x. So we have negative x over 3x squared minus xy. Now in part C, we have f of xy is x times e to the xy plus sine of a polynomial of x and y. So we'll need a few rules here when we're differentiating. So let's start with the partial derivative of f with respect to x. So to differentiate the first term in our function, x times e to the xy, we have to make use of the product and the chain rules. So using the product rule, the derivative of the first factor, x, would be 1 times our e to the xy power, and then we would add x times the derivative of e to the xy power. Well, using the chain rule, the derivative of e to some power would be e raised to the same power, but then I have to multiply by the derivative of that inner function, xy, with respect to x. So the derivative of xy with respect to x would be 1y. Then we would add, well, the sign of this polynomial term, since it is a composite function, requires the chain rule. So the derivative of sine of a function would be given by cosine of that same function. And then by the chain rule, we have to multiply by the derivative of the inner function with respect to x, which would be a 6x. So simplifying a little bit here from the first two terms in this partial derivative, I could factor out an e to the xy, and I would be left with 1 plus xy plus 6x cosine of 3x squared plus y cubed. Now for the partial derivative of f with respect to y, let's take a look. Our first term was x times e to the xy power. So if we're differentiating with respect to y, we no longer need the product rule to handle that first term, since x is being considered as a constant. So we would have our constant x times the derivative of e to the xy with respect to y would be e to the xy times the derivative of that inner function, xy, with respect to y, which would be 1x. And then plus the derivative of sine of this polynomial function would be cosine of the same function. And then multiplying by the derivative of the inner function with respect to y, we would have a 3y squared. Or simplifying just a little bit, our partial derivative would be given by x squared e to the xy plus 3y squared cosine of 3x squared plus y cubed. All right. Now let's look at an example of finding partial derivatives of a function which is defined implicitly in terms of x and y. As you recall from Calculus 1, not every function of x can be defined explicitly in terms of x, that is, as a function of the form y equals f of x. And similarly, not every function of two variables can be defined explicitly in terms of a function of x and y. So if we have an implicitly defined function by some equation, let's see how to use implicit differentiation along with partial derivatives to find the partial derivatives of our function. So in this next example, we're asked for the partial derivative of z with respect to x and of z with respect to y if z is defined implicitly as a function of x and y by the following equation. So something to keep in mind as we move through this problem is that z is actually a function of x and y. So it might be helpful when we first see our equation to rewrite it in the form x squared times z, which is actually a function of x and y, plus y times z, which is a function of x and y cubed, is equal to x plus y squared. So if we want the partial derivative of z with respect to x, let's first find the derivative, or first differentiate this equation through with respect to x. So I'll start by saying differentiating with respect to x, we would have on the left-hand side, by the product rule, the derivative of x squared would be 2x times the second factor z, I'm going to leave alone. And then we would have to add x squared times the derivative of this function z with respect to x. So I could denote that as the partial derivative of z with respect to x. Then I'm adding, well, we have a constant y times z of xy cubed. So using the chain rule, the derivative of the outer function would be 3y times z now to the second power. But by the chain rule, I've got to multiply by the derivative of the inside function, that is the derivative of z with respect to x. And this is equal to, differentiating with respect to x on the right-hand side, we would have a 1. So in order to solve for this partial derivative of z with respect to x, I want to group all of the terms involving that partial derivative on one side of my equation. Let's say this left-hand side. And I would have x squared times the partial of z with respect to x plus 3yz squared times the partial of z with respect to x is equal to 1 minus 2xz. So that 2xz term I'll move to the right-hand side since it did not involve the partial derivative that I'm after. So from here on the left-hand side, I can factor out the partial derivative of z with respect to x, and I would be left with x squared plus 3yz squared is equal to 1 minus 2xz. So finally, solving for the partial derivative of z with respect to x, we would have 1 minus 2xz over x squared plus 3yz squared. So this is the first of the partial derivatives that I was after. Now to get the partial derivative of z with respect to y, we would take the equation that we're given and differentiate with respect to the variable y. So on the left-hand side, I have a constant x squared. So since I'm differentiating with respect to y, I'm now treating x as the constant. So I've got my constant x squared times, I'm differentiating z with respect to y. So I would have the partial derivative of z with respect to y. Plus, now where I have my y times z cubed, we're going to need the product rule, since y is now a variable. So the derivative of y would be 1 times my z cubed plus the derivative of z cubed with respect to y would be 3z squared. So I have 3z squared times my constant y out in front. And then I'm multiplying by the derivative of the inner function, z, with respect to y. And that is equal to differentiating the right-hand side of my equation with respect to y. I would have 2y. So again, to solve for the partial derivative that I'm interested in, I'll group all of the terms involving the partial derivative of z with respect to y on one side of my equation. So I've got x squared times the partial of z with respect to y plus 3yz squared times the partial of z with respect to y. That's equal to 2y minus z cubed. So the z cubed term I move to the other side of the equation since it doesn't involve that partial derivative. So now from the left-hand side, I can factor out the partial derivative of z with respect to y, and I'm left with x squared plus 3yz squared. It's equal to 2y minus z cubed. So solving for the partial derivative of z with respect to y, we have 2y minus z cubed over x squared plus 3yz squared. So just as we would find derivatives of a single variable function using implicit differentiation, we could find partial derivatives of a function of two variables using implicit differentiation, as long as we're keeping track of which variable is our constant and which is the variable. So the next thing we'll consider in this section is a geometric interpretation of partial derivatives. We've said already that they represent instantaneous rates of change of a function as we make a change in one of its variables, say either x or y. But how about a geometric interpretation? Now we know that the derivative of a single variable function represents the slope of a tangent line to the graph of that function at a particular point on that graph. So let us consider a function of two variables. Suppose we have a function of the form z, which depends on two variables x and y, and the rule for this function is given by f of xy. Now this equation, the graph of a function of two variables, defines a surface in space. We'll call that surface S. So shown here below, we have this surface in 3 dimensions, outlined or shaded in gray. We're calling that surface S. Now, if we consider taking f at some point, a, b, and its value is equal to c, then that means the point, a, b, c, in space has to lie on our surface. So if we take some point in the xy plane, call it ab, or ab0 in space, and we find the value of the function at that point, and its value is c, that means that we would move upward from that point, and we would have a point P on our curve, point ABC. Now, the vertical plane defined by y equals b, so let's think about what we're doing here. If we take a vertical plane with a constant value of y, let's say y equals b, so we're passing through the point, AB0. This point would slice our surface, and the intersection of this plane with our surface would be a curve C1. So this plane intersects the surface S in a curve C1, which is parallel to the XZ plane. So an equation for that curve is z equals f of xb, and the slope of the tangent line t1 to that curve c1 at the point ABC is given by the partial derivative of f with respect to x at the point AB. So if we're considering holding y as a constant, or looking at a constant, a plane passing through a constant value of y, we define this curve C1 on our surface, and it passes through the point P on our curve. So the partial derivative of f with respect to x at this point, AB, defines the slope of the line tangent to that curve, C1, at the point P. So this is the slope of this tangent line T1. Now similarly, if we consider the vertical plane defined by x equals a, so if we force x to be a constant value, we could think about the plane passing through x equals a, so it has to pass through the point AB 0, and that plane would intersect our surface S in another curve, C2. So that plane intersects S in a curve C2, which is parallel to the YZ plane. And an equation for that curve C2 is given by z equals f of AY, where A is a constant. So the slope of the line tangent to that curve at the point ABC is given by the partial derivative of f with respect to y at the point AB. So that is the slope of this tangent line T2 to the curve C2 at the point P is given by this partial derivative of f with respect to y at the point AB. That is the slope of that second tangent line. So we have a little geometric interpretation for what these partial derivatives represent, or as we've mentioned already, the partial derivatives can be interpreted as the rates of change in the x and y directions. So how rapidly our function is changing, or how steep our surface is if we're making a change in the x direction or in the y direction. So let's look at an example involving a geometric interpretation of these partial derivatives. So we're told that we have some surface defined by z equals this polynomial function of x and y, and we're told that the plane y equals 1 intersects that surface in a curve. So the problem is to find the slope of the tangent line to that curve at the point on our surface, P, defined by 1, 1, 3. So here, let's think about which of the partial derivatives that we're looking for, with respect to x or with respect to y. Now, the curve that we're interested in is the intersection of our surface with a plane defined by a fixed y value. So if we have a fixed y value, that means that only x is changing. So we would be looking at a partial derivative of our function with respect to x. So let's start by finding that partial derivative. Here, the partial derivative of z with respect to x as a function of x and y would be given by 6y minus 2x. And we're interested in this partial derivative at a particular point P where x and y are given by 1, 1. So I'll say at the point P, defined by 1, 1, 3, we have the partial derivative of z with respect to x at 1, 1 would be 6 minus 2, or 4. And this is the slope of that tangent line to the curve of intersection of our plane with this surface at the indicated point. Now the next thing that we'll talk about in this section briefly is how to extend the concept of partial derivatives of functions of two variables to partial derivatives of functions of three or more variables. So here I mentioned briefly that the definitions for these partial derivatives can be extended to functions, say, of three variables, x, y, z, or functions of more variables, say f of x1, x2, x3, x4, and so on. And the idea is the exact same as what we had considered when we were talking about functions of two variables. If I want the derivative of a function with respect to, say, the variable x, I would treat all of the other variables, maybe y and z, if it's only a three-variable function, as constants, and then differentiate the function treating x as a variable. Similarly, if I wanted the partial derivative of a function, let's say with respect to y, if it's a three-variable function, I would treat both x and z as constants and differentiate the function using y as my variable. So given that information, let us look at the next example where we're asked to find the partial derivatives of f with respect to x, y, and z for each of the functions given. Now in part A, we have f of x, y, z is this polynomial function of three variables. So first, to differentiate with respect to x, we would treat the variables y and z as constants and then differentiate our function as we normally would, where x is the only variable. So the derivative of x to the fifth would be 5x to the fourth, plus the derivative of x to the fourth would be 4x cubed, and then I'm multiplying on the end by the constant y to the fourth z cubed. And then my term on the end, y times z cubed, well, if y and z are both constants, yz cubed is a constant, or yz squared is a constant, and its derivative would be 0. So this is all we have. Now similarly, the partial derivative of f with respect to y is found by treating x and z as constants. So the derivative of our first term, x to the fifth, would be 0, plus we have x to the fourth, and the derivative of the y to the fourth term would be 4y cubed. So if I just multiply that 4 by my constant x to the 4 out in front, I have 4x to the fourth y cubed, and then with my constant z cubed on the end, plus the derivative of yz squared with respect to y would be 1 times the constant z squared. And the partial derivative of f with respect to z would be given by derivative of x to the fifth is 0. Then I've got a plus x to the fourth, y to the fourth, which are both treated as constants, and the derivative of z cubed would be 3z squared. I just moved my constant 3 out in front of the xy terms. And then plus y times the derivative of z squared is 2z to the first, so bringing the 2 out in front of our constant y, I have 2y z to the first power. Now in part B, we have f of xyz is given by xy times tangent of x squared plus z. So let's start with the partial derivative with respect to x. So I'm going to treat y and z as constants. So I have xy times tangent of x squared plus z. So by the product rule, the derivative of this first factor, x times y, with respect to x, would be 1y, times the second factor, which was tangent of x squared plus z, plus the first factor, which was xy, times the derivative of tangent of x squared plus z. Now the derivative of tangent of a function is secant squared of that function. And then using the chain rule, we multiply by the derivative of the inner function with respect to x, which would be 2x. Or cleaning this up just a little bit, we have y times tangent of x squared plus z, plus, if I group my xy times 2x terms together, I have 2x squared y with the secant squared of x squared plus z on the end. Now for the partial derivative of f with respect to y, we're going to treat x and z as constants, and the only variable is y. So when I look at my equation, or my function, the only place that y appears is this middle term, y to the first power. Everything else, namely x times tangent of x squared plus z, is a constant. So the derivative of a constant times y would just be equal to that constant. Just like the derivative of, say, 7y would be 7, or the derivative of negative 18y would be negative 18, the derivative of x times tangent of x squared plus z, which is being treated as a constant, times y would just give us that constant value. And lastly, for the partial derivative of f with respect to z, we have a constant x times y, and then the derivative of tangent of x squared plus z, using the chain rule, would be given by secant squared of x squared plus z, times the derivative of the inside function with respect to z, which would just be 1. So here we would have the following expression for our partial derivatives. And in this next example, part C, we have f of xyz is natural log of some polynomial function of 3 variables. So using the chain rule, the derivative with respect to x is given by first the the derivative of the outside function. So the derivative of natural log of stuff is 1 over that stuff. So in this case, 1 over x squared y plus y squared z plus 2xz cubed times the derivative of the inner function with respect to x, using the chain rule, would give me 2xy plus 2z cubed. Now similarly, differentiating with respect to y, well, the derivative of log of this function is given by 1 over that function. And then by the chain rule, we have to multiply by the derivative of the inside function with respect to y now, which would be x squared plus 2yz. And lastly, our partial derivative of f with respect to z would be 1 over the same polynomial times the derivative of the inner function with respect to z, which would be y squared plus 6xz squared. So these would be our partial derivatives of that last function with respect to x, y, and z. And of course, we could extend this concept to functions of 4 variables, 5 variables, and so on. The idea is the same. To get the partial derivative with respect to a single variable, you treat all of the other variables as constant.